In a cosmos of boundless expanse and innumerable marvels, it's truly intriguing that our deepest quest is to find reflections of ourselves, to uncover that we are not alone. Just 40 light-years away, nestled within the constellation of Aquarius, lies a tiny, faint star named TRAPPIST-1. It's chilly, ancient, and barely perceptible to the eye. Yet this unassuming star hosts something quite extraordinary, not merely one, but 7 terrestrial-sized planets. It's almost as if nature itself orchestrated an experiment. Can life flourish around a star such as this? One after another, scientists have systematically dismissed most of these celestial bodies as being uninhabitable. Some are too scorching, others too frigid. Lacking in atmosphere, they offer no prospect for life. However, one particular world continues to hold immense promise, TRAPPIST-1e. And now, thanks to the invaluable data gathered by the James Webb Space Telescope, we might finally catch a glimpse of its atmosphere. What we've uncovered is truly astonishing. Could this mark the discovery of the first truly Earth-like planet beyond our solar system? Could TRAPPIST-1e potentially harbor life? Join me today as we embark on a journey to the TRAPPIST-1 star system to delve into the potential for life on its most promising planet. We'll meticulously examine new data from the James Webb Space Telescope, which has been pushed to its absolute limits, revealing the probable composition of TRAPPIST-1e's atmosphere, and whether it possesses the capacity to sustain life. That is, assuming the very star offering this chance at life hasn't already sealed its fate. TRAPPIST-1 is classified as an M-mate red dwarf. Being only slightly larger than Jupiter, it emits a luminosity 1,800 times less than our Sun, a disparity comparable to illuminating a stadium with a single candle. Although this star was initially identified in 1999, its complete planetary configuration remained undisclosed until 2017. It then gained distinction as the first and only planetary system discovered by the TRAPPIST Optical Robotic Telescope. This specialized instrument comprises 2 main components: TRAPPIST South, situated in the Chilean mountains, and TRAPPIST North, located in Morocco's Atlas Mountains. These telescopes employ transit photometry, a sophisticated technique that measures the periodic variations in a star's brightness to detect orbiting planets. In essence, when a planet passes between us and its star, a portion of the star's light is obscured, resulting in a measurable dip in its apparent brightness. Through numerous observations, these telescopes successfully pinpointed the individual orbits of multiple planets orbiting TRAPPIST-1. Initially, their data analysis only revealed the 3 innermost planets. However, additional data from both TRAPPIST telescopes as well as the Spitzer Infrared Space Telescope brought the total count to 7. Remarkably, all these planets are rocky and at least approximately Earth-sized, establishing this as the most Earth-like planetary system discovered around any star to date. For a more in-depth exploration of each individual planet within the TRAPPIST-1 system, a dedicated video is available via the link provided on your screen. However, with such a diminutive faint star at its core, is there truly any hope that these planets could be hospitable for any of these planets to receive sufficient light to sustain life? Their orbits must be considerably closer than Earth's orbit around our Sunday. Within the TRAPPIST-1 system, these planets indeed orbit much closer. In fact, all 7 are astonishingly near their star. TRAPPIST-1e completes its orbit at only 1/13th, the distance of Mercury's orbit, suggesting it could be tidally locked to its host star, meaning the same side of the planet perpetually faces the star, much like we only ever observe one face of our own moon. This has profound implications for the planet's habitability, which we will explore further in this video. More intriguingly, its orbital distance positions it squarely within the predicted habitable zone, where it receives approximately 2/3 of the energy that Earth receives from our Sunday. This precise alignment is why scientists are so captivated by this particular planet. However, life requires more than just light to flourish. TRAPPIST-1e would almost certainly need an atmosphere, which is precisely what scientists have been seeking using our most powerful space-based observatory, the James Webb Space Telescope. The teams responsible for developing the James Webb Space Telescope were granted guaranteed observation time. One particular group, the Deep Reconnaissance of Exoplanet Atmospheres, through multi-instrument spectroscopy, or DREAMS team, as they are known, immediately set their sights on the TRAPPIST-1 system. The James Webb Space Telescope is exceptionally sensitive and precise to such an extent that it can detect spectral signatures from the faint band of gas comprising these planets' atmospheres, even from a staggering 40 light-years away. It achieves this feat through a technique known as transmission spectroscopy. As an exoplanet passes in front of its parent star, James Webb not only measures the subtle decrease in brightness, but also observes how the spectrum of light changes. The telescope's near-infrared spectrometer, or NIRSpec for short, measures the wavelengths of infrared radiation closest to the visible spectrum. Molecular bonds absorb energy within this range, and distinct bonds, such as the carbon-hydrogen bond in methane or the carbon-oxygen double bond in carbon dioxide, each absorb different wavelengths. This means that by measuring precisely which wavelengths are absorbed as a planet transits its star, we can first determine if an atmosphere exists and subsequently identify the specific gases present. Acquiring data on TRAPPIST-1 has proven remarkably straightforward. In fact, the data obtained is 10 times more sensitive than that available for any other planetary system. Why is this so counterintuitively? It's because the star is relatively dim. The light obscured by a transiting planet causes a more significant relative drop in the star's apparent brightness compared to a similar planet passing in front of a larger, brighter star. A larger difference naturally is easier to measure. Using these precise measurements, the team has already ruled out TRAPPIST-1c and d as possessing atmospheres. However, the initial findings from observations of TRAPPIST-1e, a rocky planet approximately 0.9 times the size of Earth, were so captivating that scientists simply could not disregard them. It appeared this planet might in fact possess an atmosphere. This compelling evidence was sufficient for the DREAMS team to commit all their guaranteed James Webb Space Telescope observation time to further investigate. So far, they have observed 4 transits of TRAPPIST-1e with the James Webb Space Telescope. But what exactly did they discover? Well, we can begin by eliminating a few possibilities. We now understand that TRAPPIST-1e does not possess a primordial atmosphere the type a planet is born with. Such atmospheres are typically dominated by light gases like helium and hydrogen, which have not been detected around TRAPPIST-1e. These lighter gases were likely stripped away by the star's intense radiation early in the planet's life. Furthermore, it appears unlikely to have a carbon dioxide-dominant atmosphere, such as the thick and dense atmosphere of Venus. An atmosphere akin to that of Mars, which is thin and sparse, is also improbable given the recent measurements. Believe it or not, all these exclusions are positive news, as it's unlikely that any of these atmospheric compositions could support life, at least not as we currently understand it. So what kind of atmosphere does it possess? This is the crucial revelation. There could be an Earth-like atmosphere, one primarily composed of a heavier gas such as nitrogen, with a significant greenhouse effect stemming from water carbon, dioxide, or methane. Such an atmosphere, exhibiting a surface pressure of approximately 1 bar equivalent to Earth's, might be capable of facilitating sufficient heat transfer to the planet's dark side, thereby allowing for a global surface ocean despite its tidally locked state. If this were to be confirmed, it would undoubtedly capture global headlines. However, such an outcome might be overly optimistic. The current data instead leans slightly towards the conclusion that TRAPPIST-1e is a cold planet devoid of a global ocean. Accurately analyzing the data here is paramount. The ability to comprehend what we observe and its implications is the distinction between a monumental discovery and a significant error. Return to TRAPPIST-1e. As previously mentioned, an alternative to an Earth-like atmosphere exists. Elevated levels of methane, for instance, could induce a reverse greenhouse effect. TRAPPIST-1 possesses a surface temperature of approximately 2,400 Kelvin, significantly cooler than our Sun's 5,670 Kelvin, A larger portion of its energy output is shifted towards near-infrared wavelengths. Atmospheric methane is capable of absorbing this energy before it even reaches the planet's surface, subsequently re-emitting it into space, resulting in a cooler atmosphere. For the tidally locked TRAPPIST-1e, this would imply that liquid water might only persist on the permanently sunlit side of the planet. No global ocean here. However, this isn't necessarily detrimental to the prospect of life. Such conditions could potentially satisfy Darwin's warm little pond hypothesis for the origin of life. Furthermore, atmospheric modeling supports this idea. Simulations indicate that even if TRAPPIST-1e has limited water, or if its water is confined to the planet's dark side, it could still maintain a stable atmosphere. Nevertheless, this might lead to what's termed Terminator habitability, where life could only exist within a dynamic band of perpetual twilight separating day from night. However, surface water isn't the sole prerequisite. We know TRAPPIST-1e is rocky, but beyond that, details are scarce. It could be an icy, volcanically active planet with a subsurface ocean, similar to Europa and Enceladus in our own solar system. Life on Earth is theorized by some to have originated near deep-sea hydrothermal vents, and a comparable process could unfold on TRAPPIST-1e. Irrespective of where water might exist on TRAPPIST-1e, life remains a possibility. There's an energy source and potentially an atmosphere providing the fundamental building blocks for life. However, there's a significant caveat. While all these scenarios are plausible, scientists cannot yet definitively rule out the possibility that TRAPPIST-1e is merely a cold, barren, and airless celestial body entirely devoid of an atmosphere. Therefore, we must consider factors that could impede the formation of a stable atmosphere. In this particular instance, the red dwarf star TRAPPIST-1 itself is the culprit. Envision standing with me on TRAPPIST-1e for a fleeting moment. Gaze upwards. The star above us would appear more than 4 times larger than our sun in the sky. The star would glow a deep red-orange hue, casting perpetual twilight across the landscape, as if in an unending sunset, a truly breathtaking spectacle. Now, red dwarfs are intensely active stars. They produce flares far more powerful and frequent than those of our sun day. The most severe geomagnetic storm ever recorded to impact Earth was the Carrington event in 1859, an occurrence expected less than once every century. TRAPPIST-1 is believed to unleash flares of comparable power more than once every 2 days. You would likely witness solar flares arcing into space in real time. These flares carry immense amounts of energy towards a planet, enough that over extended periods, any atmosphere could be stripped away, rendering life as we know it virtually impossible. This assumes, of course, that an atmosphere was ever allowed to form in the first place. Red dwarfs are incredibly long-lived stars. TRAPPIST-1 is projected to exist for another 10 trillion years. That's 700 times the current age of the universe. In contrast, our sun is expected to endure for only another 5 billion years before it transforms into a red giant. One might surmise that given the stability and immense lifespan of a red dwarf, there would be ample time for life to emerge. However, precisely because of their longevity, their chaotic and energetic teenage years preceding their eventual quiescence are correspondingly prolonged. It is during these formative periods that some planets begin to generate their own atmospheres, gradually replacing their primordial hydrogen-helium envelopes with atmospheres composed of heavier molecular gases such as carbon dioxide, nitrogen, and methane. These chemicals are released from the planet's interior through volcanic activity. The critical issue is this: if the aggressive atmosphere-stripping phase of a star persists for too long, then an Earth-sized planet might not possess sufficient internal resources to fully establish a stable, life-supporting secondary atmosphere. The unfortunate reality is that if a planet's atmosphere fails to become established within 5 billion years, it may never form effectively, condemning the planet to a premature demise. I understand. It might seem quite disheartening for TRAPPIST-1e. And I imagine you're wondering, how can this be considered one of the most promising planets? However, we still lack definitive knowledge about whether an atmosphere has indeed survived or not. We have already observed tantalizing hints of its existence. And while the star's violent outbursts might pose a threat to TRAPPIST-1e, they could also be absolutely essential for the very inception of life. Ultraviolet radiation from flares might be crucial for creating RNA building blocks molecules fundamental to the metabolism of every life form ever discovered. Now that TRAPPIST-1 has entered its calmer main sequence phase, emitting lower levels of UV and X-ray radiation compared to its turbulent youth, there's a plausible chance for a stable habitable atmosphere to exist on TRAPPIST-1e. Furthermore, this atmosphere could be shielded from ongoing flares by its own magnetic field, much like Earth's. Earth's magnetic field originates from the swirling liquid iron within its outer core. There's a good possibility that TRAPPIST-1e possesses a similar internal system. In fact, TRAPPIST-1e's close orbit to the red dwarf could actually contribute to maintaining its magnetic field. If TRAPPIST-1e's orbit is eccentric, this would induce repeated compression and relaxation of the planet's shape. This process generates internal friction that could heat the interior by as much as 0.18 watts per square meter, which is approximately 24 times the tidal heating flux generated within Earth. We observe a comparable phenomenon in Jupiter's moon Io. Io is tidally locked with an eccentric orbit and is continuously stretched and squeezed by the gravitational interactions with the other Jovian moons, filling it with energy and making it the most volcanically active body in the solar system. So where does this leave us? Well, we might have an Earth-sized, volcanically active rocky planet complete with the building blocks for life, its own atmosphere and a magnetic field, all orbiting within the habitable zone of a relatively calm red dwarf. Alternatively, it could simply be a cold, lifeless world. So tell us in the comments which scenario you believe will eventually be confirmed. We might not get a definitive answer until the proposed Habitable Worlds Observatory, a telescope designed to search for life around stars like our own, launches in 2041. But until then, James Webb's observations remain our strongest asset. The fact that we are capable of measuring the light absorbed by a thin gaseous layer around a rocky planet orbiting a dim red dwarf star 40 light-years away is truly extraordinary, and scientists have not abandoned hope. They have gleaned insights from the initial datasets provided by the James Webb Space Telescope and refined their techniques to achieve even more precise measurements. With another 15 transit observations scheduled before December, they anticipate being able to definitively confirm the presence or absence of carbon dioxide and a secondary atmosphere, a pivotal step in the quest for life on TRAPPIST-1e. Perhaps TRAPPIST-1e and its celestial neighbors will ultimately prove to possess a uniquely inhospitable atmosphere, or perhaps one that could, in theory, sustain life. Or maybe, just maybe, we'll discover a world remarkably similar to our own home. It is truly exhilarating to uncover such immense potential for life relatively nearby, even within the confines of an extreme cosmic environment. Regardless of the ultimate atmospheric composition of TRAPPIST-1e, given the recent discovery of formations on Mars, formations believed impossible to have originated, without the presence of life, I find it difficult to shake the profound conviction that the revelation of extraterrestrial life is quite simply inevitable. The sole remaining question is when, if you enjoyed this cosmic journey and the exploration of TRAPPIST-1e, please hit the like button and consider subscribing for more deep dives into the wonders of the universe. Share your thoughts in the comments below. Do you believe TRAPPIST-1e harbors life, or is it a barren world? Your engagement fuels our exploration. If you find this content interesting, please like and leave a comment. This video from Cosmic Warning A to Z, thank you for watching.